Hi, my name is Kiwan, and today I'm going to talk about our paper, Adaptive Low Overhead Scheduling for Periodic and Reactive Intermittent Execution. First, I'm going to start by talking about what intermittent systems are. Intermittent systems refer to devices that run without a tethered power or a battery. Instead, these devices run with the energy harvested from their surrounding environment, such as RF, solar, motion, or heat. Because these systems do not require a battery to operate, they have a lot of potentials in the field where periodic battery replacement is infeasible, such as smart agriculture, wildlife tracking, or smart cities. However, intermittent systems complicate event-driven executions. An event-driven execution refers to an execution model where the program changes its state based on an external event, such as a timer interrupt or a sensor interrupt. Especially, we concentrate on two important classes of execution models: a periodic execution where a program runs periodically, and a reactive execution where a program runs timely in response to an external event. As you can easily imagine, both execution models are crucial in applications mentioned earlier. However, intermittent systems only rely on the harvested energy to run, posing challenges when the programmer wants to write an event-driven program. For example, assume that the programmer wants to collect temperature data exactly every 10 seconds. The system may or may not be able to do so because it simply may not have enough energy to collect the temperature data when it needs to. To put it in a more formal way, intermittent systems may fail to achieve event-driven execution because it lacks control over when energy becomes available. And that is the main challenge CatNap tackles. So this is going to be the overview of the rest of my talk. First, I'm going to talk a little bit more about the operation of an intermittent system. Then I will explain why supporting event-driven execution is hard. Then I will introduce our CatNap system, the evaluation result, and conclusion. So first, I will explain how an intermittent system usually works. An intermittent system usually consists of an energy harvester such as a solar panel, a microcontroller, sensors such as a microphone, and energy buffers, which are usually capacitors where these devices store their harvested energy temporarily. On the right side, I will show you the energy stored in the energy buffer of the system over time. When the device does not have enough energy in its energy buffer, the device is inactive. The device charges up its energy buffer using its harvester until enough energy accumulates. This is when the device becomes active and starts to run a program. Usually, running a program quickly depletes the energy buffer and the device again becomes inactive. And this repeats indefinitely. So I've explained how an intermittent system usually works. Now I will explain in more detail why implementing an event-driven execution is hard on top of these devices. Again, we focus on periodic and reactive execution mainly. And due to the interest of time, I will mainly focus the discussion around the periodic execution in this talk. For the challenges with reactive execution and how CatNap tackles reactive execution, please read our paper. So why is it hard to run program periodically on intermittent systems? First, varying incoming power makes periodic execution complicated. Let's again say that the programmer wants to collect the temperature data every 10 seconds. This may be simple when there is enough energy, as you can see from the figure. However, when the incoming power becomes less, the charging time of the system becomes longer, and this can make the system fail to keep up with the programmer's specified period. One possible solution to this is reducing the quality of the program. For example, a program might choose to collect a less accurate sample while using less energy and thus keeping up with the programmer's specified periodic requirement. This is possible because many sensors can be configured to use less energy while being less accurate. Another problem can occur when multiple code are being executed concurrently. For example, one might write a program that collects data every 10 seconds and concurrently compresses the data. In such a case, when the system uses too much energy on compression, The system may fail to collect the data at the right moment because it might not have enough energy left in the buffer. And again, this will result in a violation of the user-specified period. This problem can be solved with smart scheduling. Instead of using too much energy right before the data collection, if the system had spreaded the compression at the right moments in the program, the system would have run correctly, as you can see from the right figure. Now, I've explained the challenges and possible solutions for realizing an event-driven execution on intermittent systems. On top of the discussion, I will next introduce our system called CatNap. CatNap consists of four key components. The programmer writes a CatNap program and the scheduler executes it. The feasibility test checks whether the program is schedulable, and CatNap runs the degradation logic when it is not schedulable. First, I will talk about CatNap's programming model. CatNap requires the programmer to write a program as a collection of events and tasks. Events are code that has a time requirement. Code that must run periodically or reactively should be declared as an event. Events run atomically and must be kept short. Usually, things like sensor read or a communication must become an event. Tasks, on the other hand, are code without a time requirement. They can be long, and they can be interrupted by an event or a recharge. Tasks usually hold computations. This example shows a sample program in CatNap, where it collects temperature data every 10 seconds, sends them to a task that compresses them, and transmits the result to the server every minute. Tasks and events communicate the data with a FIFO queue defined between them. In CatNap, the programmer can also specify how the program can be degraded in case the incoming power is too low to keep up with the schedule. For example, the programmer can hint the system to decrease the frequency, the quality, or even run an alternative code that uses less energy. The programmer defines events and tasks just like a C function. Events or tasks can be initiated by other events or tasks, or can be run periodically with a programmer declaration. You can see more details about the CatNap syntax in the paper. Now, I will explain how CatNap scheduler runs the events and tasks written by the programmer. First, CatNap dynamically measures the energy used by each event and also measures the incoming power to calculate the time needed to recharge the energy each event uses. Then, CatNap separates the energy buffer using a programmable circuitry so that it has a separate energy reserve just for events. The energy in the reserve is only used by events and never by tasks. The size of the reserve is set dynamically to be larger than the sum of the energy used by all the events defined. Then, the CatNap scheduler schedules events, tasks, and recharges with different priorities. CatNap runs events with the highest priority as soon as they arrive. When the energy reserve for events is not full, CatNap prioritizes recharging the buffer over running the tasks or recharging for the tasks. I will show you how CatNap scheduler works with an example. In this energy buffer diagram, I added a threshold showing the reserve for events as a green line. The energy below the green line is reserved for events, while the energy above can be used by tasks. As said earlier, events run immediately as they arrive. When the reserve for events is not full, CatNap prioritizes recharging it over running tasks. And tasks only run with energy over the energy reserve. However, as you can see from the diagram, tasks never uses reserved energy for events. Because there are always energy reserved for events, events can always run as soon as they arrive. We prove in the paper that when a set of events and recharges are schedulable, CatNap's policy can always run the program correctly. However, this sentence might pose a question. How would you know if events are schedulable? Also, what happens if they are actually not schedulable? To answer the questions, I will introduce the feasibility test and the degradation logic of CatNap. A feasibility test determines if events can run with the user-specified scheduling requirement or not. The main idea of the feasibility test is checking whether a set of events will use more energy than what can be recharged. We developed a mathematical formula to test the schedulability with a given input power. Of course, you do not need to digest the formula right now. If you are interested, a full proof of the feasibility test is provided as an appendix. Because the incoming power changes over time, CatNap dynamically measures the incoming power and runs the feasibility test periodically. When the task passes, CatNap scheduler simply runs events and tasks according to their priority and it will run correctly. When the feasibility test fails, CatNap degrades the event quality to meet the schedule. Again, the degradation is guided by the user annotation as we've seen in the earlier slide. CatNap degrades events until they are again schedulable with respect to the given input power. For more details on CatNap, including CatNap support on reactive execution, please read our paper. Now, I will show you some evaluation results to show you that CatNap implements periodic execution while imposing moderate overhead. We conducted several evaluations to show the effectiveness of CatNap. We ran several event-driven benchmarks with different combinations of various event-driven workloads running concurrently. We also performed an overhead analysis and measured its robustness against short and long-term power fluctuations and also measured the accuracy of the feasibility test. We also conducted a case study of a particle filter for chipset orbit estimation. In this talk, I will concentrate on the three interesting results. You can find more details about other results in our paper. To show that CatNap enables periodic execution, we first ran a benchmark that periodically samples a block of audio data where the number of samples in each block can vary. We ran the evaluation on a real energy harvesting setup where the device harvested RF energy from an RF receiver antenna. We compared with INC, a recent system also targeting event-driven execution on intermittent systems. For CatNap, the audio sampling was programmed as an event. This graph shows the resulting period of the actually sampled block. On the x-axis, different incoming power configuration is shown. For each configuration, the period of the actually sampled block is plotted for CatNap and INC. The target period is specified by the programmer and is shown as a red line. It is a good system if the bar is close to the red line. As you can see, CatNap meets the period requirement in all the incoming power, while INC violates the requirement heavily when the incoming power gets smaller. CatNap meets the periodic requirement nicely because it dynamically decreases the number of samples in each audio block, which is the quality knob the system can control. On the x-axis in this figure, again there is different configurations of the incoming power. And on the y-axis, the number of samples per block is shown. The number of samples in the block is a controllable quality and it is higher the better. As you can see, CatNap degrades the system quality as the incoming power gets less. However, INC always tries to use the highest quality, leading to periodic requirement violation as we've seen from the earlier slide. Next, we concurrently ran a periodic workload of measuring the temperature every 0.56 seconds and a compute-intensive workload of downsampling the data with a square filter. Again, we ran the evaluation on a real energy harvesting setup and compared with INC. For CatNap, the periodic temperature sensing was programmed as an event, while the downsampling was programmed as a task. This graph shows the resulting period of the actually sampled data. On the x-axis, again different incoming power configuration is shown, and for each configuration, the period of the actually sampled data is plotted for CatNap and INC. The target period specified by the programmer is shown as a red line. As you can see, CatNap meets the period requirement in all the incoming power again, while CatNap violates the requirement heavily when the incoming power gets less. CatNap meets the periodic requirement nicely because the downsampling task does not touch the energy reserve for the temperature measuring event, and the temperature sensing event can always run whenever it is required. CatNap had low scheduler overhead. The time overhead of running the scheduler varies with the number and the frequency of events. However, in a realistic setup, the time overhead was less than 1%. The memory overhead, on the other hand, was around 50% compared to Ink. The memory overhead was mainly due to its large library code size. Now, I will summarize my talk. Prior intermittent systems could not support periodic and reactive executions reliably. CatNap enabled event-driven execution by providing a new event and task-based programming model using a recharge scheduler and separating the event energy reserve, and finally running a feasibility test based on measurements and doing controlled degradation. CatNap enables much reliable periodic and reactive execution compared to prior work. This is the end of my talk. Thank you, and if you have any questions, feel free to ask.